In this lesson, we will discuss divisibility and we will define the division algorithm. Let's begin with divisibility. For integers a and b, we say a divides b written as a with a vertical line and then b. We say a divides b if b equals a times c for some integer c. Now notice that this is not a fraction. So often when you hear the word divisibility or divides, you think of it as a fraction, but this actually is written as, so you think of it as b is an integer multiple of a. Okay, so that's what it means for a to divide b. It's nice not to have fractions in your definitions of divides because we don't have to worry about dividing by zero. And in fact, according to this definition, 0 could actually divide another number like 0. So 0 divides 0 in this definition. Well, if a divides b, we have a couple other words I want to define. We say, so in this case, we say a is a factor of b. Okay, so when we say factor, that saying a divides b is the same as saying that a is a factor of b. We say a is a divisor of b, and that b is a multiple of a. So for example, 3 divides 12 because I can write 12 as a multiple of 3. Because 12 equals 3 times the integer 4. But to say something does not divide, we just simply put a slash through the divide symbol. So 5 does not divide 12 because you cannot write 12 as an integer multiple of 5. So here are some facts for integers n. First, n divides 0. Why is that true? Well, for n to divide 0, we have to be able to write 0 as n times an integer. Well, 0 is n times 0. So any integer we see it divides 0. That again includes the number 0. 0 divides 0. 2. Another fact, number 1 divides n. For every integer n, 1 is a divisor. So in particular, every integer has at least one divisor, namely 1, because I can write n as 1 times n. Third fact, every integer divides itself. So n divides n. Well, can I write n as an integer multiple of n? Yes, n is n times 1. So we see that these facts are pretty obvious, but we can use these facts in the future. Now, I mentioned that every integer has at least one positive divisor, the number 1, but we want to define a special type of integer that has exactly 2 positive divisors, and we call these numbers prime. Here's our definition of a prime number. A natural number let's call it P, is prime if it has exactly 2 positive divisors. The numbers 1 and the number P itself. Okay? So just as a note, by this definition, we do not consider the number 1 to be prime. So 1 is a natural number, but it has only 1 positive divisor itself. So we never include 1 in the set of prime numbers. 1 is not prime. Okay? So every natural number other than 1 is either prime and has exactly 2 positive divisors, or it will have more than 2 positive divisors, and we call these numbers composite. So here's our definition. Here's our definition of a composite number. Any natural number greater than 1 that is not prime is called composite. So the number 1 itself is, again, not composite. So every natural number is not either prime or composite, but every number greater than 1 is either prime or composite. And by our definition of prime, it must be that every composite number has more than 2 positive divisors. So every composite number has more than 2 positive divisors. We know that every natural number other than greater than 1 has at least 2 positive divisors, 1 in itself. If it has another one, then it's clearly composite. So let's look at some of the theorems that we can prove using this new definition of divides. For integers a, b, and c, such that a divides b and b divides c, then we can conclude that a divides c. Here's the proof. Well, since a divides b and b divides c, we can use the definition of divides to write equations for b and c. So since a divides b and b divides c, there exists integers, let's call them d and e, such that b equals a times d and C equals B times E. Okay, so that's the definition of divides. We can write, if A divides B, then I can write B as A times some integer. Likewise, C equals B times some integer. Well, then C, which we know equals B times E, also equals AD times E, because we know that B equals A times D. But this looks like A times the integer DE. So I've just written C as A times some integer. Thus, A divides C. So in this previous theorem, I used the fact that if D and E were integers, then D times E is also an integer. So is this always the fact? Is this always the case that if you multiply two integers, do you always get another integer? Yes. So this is a fact that we will use in our proofs, that when you multiply integers, you still have an integer. In fact, for all integers A and B, this works as well with addition and subtraction. So for integers A and B, A plus B, A minus B, and A times B are integers. The fancy way of saying this is that the integers are closed under addition, under subtraction, and under multiplication. So this is kind of a fancy way of saying that whenever you add two integers, the result is still an integer. If you subtract two integers, then the result is still an integer. If you multiply two integers, you still have an integer. And this also works for combinations. If you combine addition, subtraction, and multiplication with all integers, then the result will still be an integer. So this fact will be used in future proofs. Let's look at another theorem about divisibility that we'll use later. Now, A, B, C, M, and N are all going to be integers in this theorem. Okay, so if A, B, C, M, N are all integers, and if A divides B, and A divides C, then A actually divides any integer linear combination of B and C. So what does that look like? So A divides any expression that looks like an integer times B plus an integer times C. Okay. So an expression like MB plus NC is called a linear combination of B and C. So let me write that down. A divides any linear combination of B and C. Okay. So again, we'll use our definition of divisibility for our proof. Since A divides B and A divides C, we can write B as an integer times A, and we can write C as an integer times A. So B will equal A times some integer D, and C will equal A times some integer E. Okay, that's the definition of divides. Now look at the integer linear combination MB plus NC. I'm going to replace B and C with the expressions in the last sentence. So MB plus NC equals M times AD plus N times AE. Now, both of these terms have a common factor of A, which I'm going to factor out. So I'm going to factor out an A. From the first term, I'm left with the factors M and D. In the second group, I'm left with the factors N and E. But we just said that if you have integers and you add and multiply integers, the result is an integer. Therefore, MD plus NE is an integer, and we've written MB plus NC as A times an integer. Therefore, we can conclude that A divides the quantity MB plus NC. So this is an important result which we'll use in future theorems. So if A divides B and A divides C, then A divides any linear combination of B and C. So we defined prime numbers and composite numbers. Some other classifications of numbers that often occur in number theory are even and odd. So we can define an even integer to be an integer who has 2 as a divisor. So our definition, I don't want to define integer using another word, divides. So we're going to define an integer to be even. So an integer n is even if I can write n as 2 times an integer. So if n equals 2 times a for some integer a. And so we see that looking at the definition of divides, 2 does divide n. Okay? Or we could say that n is a multiple of 2. So this is our definition for an even integer. Let's define odd integers similarly. Well, if an even integer is a multiple of 2, we'll define an odd integer to be 1 more than a multiple of 2. So an integer n is odd if n equals 2a plus 1 for some integer a. Okay? So let's look at some theorems about even and odd numbers. Suppose x is an integer. then if x cubed plus 1 is even, then x is odd. Okay. So if we try to prove this directly, you might try to start off your proof assuming that x cubed plus 1 is even. And then by our definition, you might try to write something like x cubed plus 1 equals some integer 2a, 2 times some integer a. The problem with this is that we're trying to conclude that x is odd. To get an equation involving just x, it looks like we're going to have to deal with some cube roots or something because we have a power of 3 on x. So a direct proof of this statement would not be the most efficient way. What I would recommend is using the proof technique called the contrapositive. So we're going to try to prove the contrapositive statement. The contrapositive of if x cubed plus 1 is even, then x is odd, would be the statement if x is not odd, then x cubed plus 1 is not even. And since every integer is either even or odd, we could also think of it as the statement if x is even, then x cubed plus 1 is odd. So that's the statement that's easier to prove. So we're going to prove this using the contrapositive, or proof by contraposition. So suppose that x is not odd. Then x must be even, and by definition of even, we can write x as 2 times some integer a. Now let's use this expression for x in the quantity x cubed plus 1. Then x cubed plus 1 equals the quantity 2a cubed plus 1. Now this expression definitely looks odd to me. So, but to make it look exactly like our definition, 2 times an integer plus 1, I'm going to factor out one of the 2's from this expression. So I'm going to rewrite this as 2 times what integer? Well, if I had 3 factors of 2, if I factor one out, I'm left with 2 factors of 2, which is equal to 4, and I have 3 factors of a. So 2 times 4a cubed plus 1. Well, this does look like 2 times an integer plus 1, so we can conclude that x cubed plus 1 is odd. And since it's odd, it's not even. So we've proven the contrapositive of the statement that if x is not odd, then x cubed plus 1 is not even. Therefore, if x cubed plus 1 is even, then x is odd. The next theorem involves the definitions for even and divides. Suppose a is an integer. If a is even, and 7 divides a, then I can conclude that 14 divides A. Let's use the assumption that 7 divides A. Since 7 divides A, we can write A as 7 times an integer. So I'll write it as A equals 7 times B for some integer B. But we also know that A is even. Since I've written A as 7 times B, and I know A is even, it must be true that B is even. Because since 7 is odd, it can't have a factor of 2 in it. So B must be even in order for the whole product, 7 times B, to be even. So since A is even, and 7 is odd, it must be true that B is even. If B is even, I can write it as 2 times another integer. Then B equals 2C for some integer C. Let's put this all together. Then A, which equals 7B, equals 7 times 2C, substituting in for B, and 7 times 2 is 14. So I've written A as 14 times C. Then by definition, 14 divides A. The following theorem is called the division algorithm. Given integers A and B, with B positive, there exist unique integers Q and R for which A equals Q times B plus R with R between 0 and B. So R is greater than or equal to 0 and strictly less than B. The letters Q and R stand for quotient and remainder. Okay. As a note, we use Q to stand for quotient, and R is called the remainder. When A is divided by B. So let's see an example of division algorithm before we discuss a proof. So think about division. Say I wanted to divide 37 by 5. So b equals 5 goes into a, which is 37, a total of 7 times. So the quotient q is 7. So 5 goes into 37 7 times with a remainder of 2. So you might think of it as, if you're doing long division, 37 divided by 5 goes in 7 times, multiply, subtract, you get a remainder of 2. But the division algorithm says we can write 37 as 7 times 5 plus the remainder 2. So just rethinking how you write division. Instead of saying 37 divided by 5 equals 7 plus 2/5. If you just multiply both sides of this equation by 5, you get the statement for the division algorithm. 37 equals 7 times 5 plus 2. So we will use the division algorithm when we're working with greatest common factors, or greatest common divisors of integers. So now let's talk about the proof of the division algorithm. First, we want to show that at least one pair Q and R exists. In the statement of the division algorithm, it says that there's a unique pair of integers Q and R that satisfy those statement. So let's show that there's at least one pair, and then we will show that these pair are unique. So first, we show that at least one pair Q and R exists. Let's consider the set S containing all integers of the form A minus n times B. S is the set of all integers of the form A minus nb, where n is an integer. So written in set builder notation, S equals the set of A minus nb such that n is an integer. Well, this set S will contain non-negative elements. And then we're going to use the well-ordering principle to show that there's some smallest non-negative element of this set S. So let's show that S contains non-negative elements. Well, if A is non-negative, so if A is greater than or equal to 0, then A minus -1 times B will equal A plus B. And if A is non-negative, and we assume that B is positive, then A plus B is in this set, and A plus B is positive. Okay, so if A is non-negative, A plus B is positive and in S. So therefore, S contains a non-negative element. But if A is negative, then A minus NB will eventually be positive if I choose a large negative integer n. Because remember, B is positive. So if I plug in a large negative number for n, then A minus the negative n times B will be positive. So this will be positive. In fact, if I choose any integer n less than A over B, then A minus NB will be positive. Since n goes through all integers, this will occur. This element will be in S. So we've shown that S contains non-negative elements. Okay. Well, by the well-ordered principle, we know that S must have a smallest non-negative element, and we're going to call that R. So by the well-ordering principle, S contains a smallest non-negative element, we're going to call this smallest non-negative element R. Then the number Q will be the corresponding value of n for this smallest R. So I'm going to let Q be the corresponding value of n to R. So in other words, every element of S looks like A minus NB. So R is one of these combinations, A minus NB. I'm going to let Q be that number, that integer n. So I can say that A minus QB equals R. Well, using this equation, if I add QB to both sides, I see that A equals QB plus R, and we assumed that R was non-negative. This almost meets all the necessary conditions for Q and R. What remains is we need to show that R is strictly less than B. If I can show that R is less than B, then we'll have shown that at least one pair Q and R satisfies the criteria of the division algorithm. So, for a contradiction, suppose that R is not less than B. So let's suppose R is greater than or equal to B. Then if I subtract B from both sides of this expression, R minus B is non-negative. And I'm going to show that R minus B is also in the set S, and since B is positive, R minus B will be less than R, and this will contradict the fact that we assumed that R was the smallest element of S. So since R minus B is greater than or equal to 0, and I can write R minus B as A minus Q plus 1 times B. So just to verify that this equals R minus B, let's multiply this out. So I get A minus QB, which is R, minus B. So this does equal R minus B. So I've written R minus B as A minus an integer times B. So that proves that R minus B is an S. And R minus B is smaller than R. So I just showed that R minus B is a smaller non-negative element of S than R. But this is a contradiction because we had defined R to be the smallest one. This contradicts R being the smallest non-negative element of S. Therefore, our assumption that R was greater than or equal to B is false. And we can conclude that R is less than B. And that satisfies all the necessary conditions of the conclusion of the division algorithm. So A equals QB plus R with 0 less than or equal to R is less than B. So we've shown that at least one pair of integers Q and R exists satisfying the conditions of the division algorithm. Now we need to work on the uniqueness statement, that there's actually only exactly one pair, Q and R, that satisfies these conditions. So now we will show uniqueness. To show uniqueness, let's assume that there's another pair that satisfies the conditions of the division algorithm. So we will assume that A equals, let's call it Q prime times B plus R prime, and Q prime and R prime also satisfy the conditions that R prime is greater than or equal to 0 and strictly less than B. What I'll show is that Q prime has to equal Q and R prime has to equal R. So we've shown that uniqueness. Well, then since A is equal to QB plus R, and A also equals Q prime B plus R prime, I can obtain the equation QB minus Q prime B, that will equal R prime minus R. Now I'm going to factor out a B from both sides of this expression. So B times Q minus Q prime equals R prime minus R. Look at this expression. It looks like R prime minus R is an integer multiple of B. In other words, B divides R prime minus R. Okay, so B divides R prime minus R. But R prime minus R is less than or equal to R prime. Okay, because if R prime minus a non-negative number, R, will be less than or equal to R prime by itself, but we assumed R prime is less than B. Okay, so I've shown that R prime minus R is strictly less than B, and I will show that R prime minus R is strictly greater than negative B. So negative B is less than negative R, and if I add R prime, which is non-negative, this is negative R will be less than R prime minus R. So let's combine these two inequalities. Then negative B is strictly less than R prime minus R, which is strictly less than B. But recall, we said we already concluded that B divides R prime minus R. The only multiple of B that's between negative B and B is the number 0. So let me replace R prime minus R with this expression B times the quantity Q minus Q prime. So in this expression, we get negative B is less than b times q minus q prime, which is less than b. And so you see in the middle of this inequality, we have a multiple of b that's between b and negative b. But the only multiple of b between negative b and b is 0. Therefore, b times q minus q prime has to equal 0. Which implies, since b is positive, that q minus q prime equals 0, and therefore q equals q prime. If q equals q prime, then r prime minus r also equals 0. Which implies that r prime equals r. This proves uniqueness. And concludes the proof of the division algorithm.